of lectures. If not, then we'll start with the next lecture. So when I want to put lectures on the web, actually, so for example, last lecture was lecture 4, but it did go into 2 parts. We covered the quantitative part of atmospheric in one lecture, and the next lecture we covered is coherence and research. So they will be part of the same. This lecture is still called as lecture 5. And earlier was called as lecture 4, was lecture 4 2. Okay. So by now I expect that all of you are comfortable with vacuum oscillations. So it's reasonably straightforward stuff. The level eigenstates E and U, mass eigenstates which we call U1 and U2. What we do is we start with the flavor eigenstate, we separate it into mass eigenstates, superposition. Then we let them propagate. When they propagate, they gain some phase depending on the mass, and finally we see them integrate. So this is the straightforward idea of vacuum oscillations. Where we want to reach today is to reach to a place where we can talk about neutrino oscillations when they pass through matter, the matter of constant density. So before we do that, it would be good to be able to say the same thing that we said earlier in terms of language of matrices. So now onwards, matrices are going to be very crucial. Okay? As you realize, the large part of this course is going to be about diagonalizing matrices. Diagonalized matrices should take their eigenvalues, eigenvectors, blah blah blah, and that is going to be sort of important part of this course. So what I will do today is the following. So we will talk about how to write down effective Hamiltonian in the 2 neutrino system. Okay? So till now we only saw effective Hamiltonian in 1 neutrino system, which we said was n square by 2e. So we will go with this formalism with vacuum. Then we will look at vital potential for neutrinos. So at the end of this, we will try to look at 2 different situations. It will turn out that vital potentials are important if you want to look at evolution due to mixing between UE and mu. Right? It will also be important if you want to talk about something called as sterile neutrinos, which we will come to later. So we will try to cover these parts in presentation. So let's go slowly. Each part is important because next part builds on it. If you have any minor question also, just stop me and ask me questions. So this sort of should be great. Okay, so let's first talk about effective Hamiltonian in vacuum. So take a neutrino mass eigenstate, and as we saw earlier, so clearly if you want to see how a nu1 propagates and still says nu1, it basically travels as its effective Hamiltonian is effectively P plus m1 square by 2p. When m1 is the mass of nu1, okay, and that's h11. H11 is the element Hamiltonian that takes nu1 to nu1. Similarly, h22 element will take nu2 to nu2, and that will be P plus m2 square by 2. Right? The mass eigenstates travel independently, so they don't mix. So therefore, you won't have any h12 or h21 element. Okay? If you take h as a 2 by 2 matrix, in the basis of mass eigenstates, there will not be any off-diagonal elements. This is the definition of mass eigenstate. Mass eigenstates are just the eigenvectors of Hamiltonian. So therefore, if I want to write the Hamiltonian in the mass basis, this is what it will look like. So this is the Hamiltonian. I will have at h11 and h22, I have these 2 numbers, which is m1 square and m2 square by 2e. And this is going to be my effective Hamiltonian. Okay. Now, I write it in this form. So what I do is I take out the identity part from it. And so I take out P, which is common to the 2, and I take out the average of these 2 n square by 2 each, m1 square by 2 square by 2. If I take these things out, what remains is this matrix, where delta is m2 square minus m1 square divided by 4. which is like delta n square by 4. The reason I do it is similar to the reason we saw earlier in the case of vacuum oscillations. The reason why we don't keep the momentum, we are trying to look at oscillations of neutrinos with a given momentum. And we saw that when we calculate the probability of survival, this momentum term always cancels out. It's e power ip from 1 and e power minus ip from 1. They always cancel. So whenever you have got such constant terms, they will always cancel out in the spaces. So here, for example, therefore, if I have this p, and if I keep this p in the effective Hamiltonian, you will get e power ip t for mu1, e power ip t for mu2, and always when you take the inner product of mu and mu, some neutrino that is travel, they will cancel. So therefore, the physics of mixing is only relevant for that part which is not a constant, or not a simple number. Yeah, so maybe so what do we do? So usually what we do, take mu1. Someone shifted, and I did it like this. So let me try. Wonderful. Let me get used to it. Let me see if there is some way of. So I cannot see what I am writing. Okay, but I will try to write without seeing. So usually what happens? My new one propagates as e power minus I h t nu. This is what I normally do. And then I say that this is e power minus I p t and e power minus I, and there is n square by 2t times t, and this is nearly equal to. So yes, in fact there is a phase which is e power I p t. However, what happens finally when I want to calculate a probability? So probability of let's say mu going to mu. I have to take inner product of let's say mu and whatever happens to this mu at time t, and I take mod square of this. So now this e power I p t is going to remain as a constant. Okay, so it will be there in this mu of t. It will also be there in this mu. And therefore, whether I keep it or don't keep it, my answer will not change. So, if the only quantity I am interested in is this p mu, then it will not change whether I keep this p or not. Okay. Similarly, now there is this e power minus I n square by 2 dt. Okay. And then let's say my mu2 was e power minus I p t and e power minus I m2 square by 2d times t. Now, of course, I keep it as m1 square by 2 and m2 square by 2d. Okay. But let's say instead of this, I decide to multiply this thing by a constant, which is e power minus I, and this is what it is, m2 square plus m1 square by 2d. And this also by the same one, e power minus I, m2 square plus I do this. This is just a constant times t. Okay, but the phase that I give to mu1 and mu2 is the same. Then again it won't matter, because finally when I am going to take the inner product and mod square, such a constant phase that I give, constant and equal phase that I give to mu1 and mu2 will always cancel. So therefore, in the sense of this effective Hamiltonian, what this means is that if I take identity out of the Hamiltonian, take that part out, which is the same for mu1 and mu2, then my probabilities will not change. Okay? I will do it many times today, so this is an important point that people should agree on. Okay? if I get a Hamiltonian, okay, so let me give you very random. Okay. So if I take a Hamiltonian which looks like 3, 4, 5, 6, and if I want to see its evolution, okay, this should be the same. If I take instead of 3, 4, I take 1 and 2, 5, 6. So what I've done is I've taken out identity from 3. So I've taken out 2 from here and 2 from here. So I've basically taken out, it's at 2 times identity. So 1, 0, evolution that I get by using 3, 4, 5, 6 is the same as the evolution I will get using 1, 2, 5. So these constants only appear as phases. These phases are not measurable in any oscillation experiment, therefore they don't matter. So you can always keep them, but they will be in messy algebra. To simplify things, algebra will be simple. Okay, so therefore we always have this constant part kept outside. Okay, so therefore, if I am allowed to keep these constant factors out, my effective Hamiltonian becomes very simple. It simply looks like this. So, constant is kept out, so H effective is minus delta and delta. So delta is delta n square by 4. I will keep on using this delta throughout. So in terms of delta, all the oscillation parameters are probably look like this. So this is my effective Hamiltonian in a 2-flavor system. Everyone with me so far? So what do you do with this? If you have Hamiltonian, you should use that to see the evolution of your state. And we know that if you have a state, then we can write Schrödinger's equation. So our state is this, I. So nu1, nu2 is our state. So this is like writing I d by dt of psi is equal to h psi. It's standard Schrödinger's equation. So now we can write it in terms of our 2 states, which are nu1 and nu2. Now what will happen? This means that the solution is, okay, so you are writing things like I d by dt of psi equal to h psi. So h is the constant. This delta was the constant. So if h is the constant, then so h constant implies my psi of t is e power minus I ht times psi of 0. So this is the simplest kind of evolution equation that you can solve. So I apply the same thing to this particular this Schrödinger's equation. So what does it look like? So this means that I have to take e power I this quantity times time. So let us look at it. So therefore, my nu1, nu2 is going to be exponential of I times minus delta 0, 0 I h t times u1, 0, u2, 0. And since there are no off-diagonal elements, this is just a very simple thing to exponentiate. So this is simply equal to e power minus that. This is I delta t, e power minus I delta t, 0, 0. Because we had a diagonal matrix to exponentiate, it's very simple to exponentiate that matrix. Once the off-diagonal element thing will become messy, you have to use power series. So if you know how to exponentiate the matrix, you write a power series like you do for. However, for diagonal matrices, the power series is very simple, and therefore you can only write this exponent. So what has happened now? So we actually know how to write down nu1t in terms of nu1, 0. This is nothing new. I mean, if I write it down what will it look like? Looks like u1 of t is e power I delta t times u1 0, and u2 of t is e power minus I delta t times u2 of t. So that what it will look like is u1 of t is e power I delta t times u1 0, and u2 of t is e power minus I delta t. So we know how mass eigenstates form. Then you do the same exercise that you did earlier. So let's say you produce new mu. So you produce a new mu. So mu at 0 was nu, which was some cos theta mu1 plus sin theta mu2. Then you want to say what happens when what happens to mu at time t. So this will therefore be cos theta of u1t plus sin theta of u2t, and I am following exactly what we did earlier. So we know what u1t becomes. So this is cos theta times e power pi theta t of u1t plus sin theta e power minus I delta t.
u1 0.
This is u1 0. Oh, sorry. And finally, I want to first calculate what part of mu is that. So I do mu t inner product, and I will basically get cos square theta e power I delta t plus sin square theta e power minus I delta. I am doing nothing great. We actually did this in a different language last time. So I might make e mu is mod square of this. So when I mod square this, I get cos to the power 4 theta. This gives me sin to the power 4 theta. Plus, when I take inner product, here I get 2 times cos square theta sin square theta times so I should get a cosine thing, cosine of theta. So if you go back and look at some of our earlier calculations, you will see that thing will do exactly the same. So let me see if in these notes I can go back and quickly look for where we had this. Okay. So see, when we did this earlier, we had exactly cos to the power 4 theta plus sin to the power 4 theta plus 2 sin square cosine square cos of this quantity, which is just 2 times delta times t. So we have done nothing new. Okay, delta is just a new convenient language to use. So therefore, we can now do everything that we did earlier in terms of data. So probability will now look in a much simpler form. So then essentially I get probability of mu is 1 minus sin square 2 theta sin square of theta. Delta is square by 4 times t. This is something you write here. So this was evolution in mass basis. Because mass basis is very easy to evolve. So now let's see what to do in terms of flavor basis. So very often we create things as flavors, muon, tau, or e. We detect them as flavors. Okay. So it's good to see how things work in terms of flavor basis. So we now have to go from mass to a flavor basis. Okay. So if I want to go from mass to a flavor basis, I use this mixing matrix. Okay. So right now, just look at this part. So alpha, beta flavor eigenstates, mu1 and mu2 are mass eigenstates. This is a rotation matrix. This rotates by an angle theta. Okay. So cos theta, sin theta, minus sin theta, cosine theta. Simple standard rotation matrix. So I say that I go from mass to flavor basis by rotating through an angle theta. This matrix I often call as U. Okay. U stands for unitary because it's a unitary matrix. Result. So I say that my mu alpha mu beta is U times mu1 mu. And U will be always given this. Then I want to go the other way around. So I want to be able to write down my mass eigenstates in terms of flavor eigenstates. So my mass eigenstates will be U dagger, which is the inverse of this matrix. So it basically changes the sign of this sign here. So this just becomes mu1 mu2 is U dagger times mu alpha mu. So now in two flavors, we know very easily how to jump between different mass eigenstates. So what happens now? The evolution. Now we knew that evolution of mu1 mu2 is simply like this. Now we want to find the evolution of mu alpha mu beta. So how does that happen? So we know that mu1 mu2 E is equal to e power I delta t e power minus I delta t equals 0 times mu1 mu2. All we need to do is now write this thing down in terms of flavor eigenstates. Okay. Now I know that mu1 mu2 is U dagger times alpha beta. So I write this as U dagger times mu alpha 0 mu beta. Right. This remains the same. So I delta t minus I delta t equals. This equal to again u1 t u2 t is U dagger times mu alpha at t mu beta. So all I have done is to write this thing in terms of equal. So now what happens? So I pre-multiply this by u. So then I get mu alpha at t, mu beta at t is equal to u times e power I delta t, e power minus I delta t equals 0, u dagger times mu alpha at 0, mu beta. So what has happened now? I have written down an equation for mu alpha mu beta that looks very similar to other equation, except that now this is my Hamiltonian. This is the Hamiltonian flavor basis, so I will always call it HF in somewhere. F stands for flow. So just like in the mass basis we had this Hamiltonian, in the flavor basis we have this Hamiltonian. Now this is a complicated beast because you have some sin theta, cosine theta, you never have some sin theta, cosine theta. So it's complicated. However, we know how to write it down because at some point in future we will need to write down Hamiltonian in different bases. So this is going to be the Hamiltonian in the flavor basis. Hamiltonian in flavor basis. So in principle, you may not even have to go through this process. This is what we did. We took mu, we said we'll go to first mass basis, use the evolution, and again come back to nu. In principle, you want to do that. And so the Hamiltonian, what simply you can do is take this and calculate e power minus I hf times t, and you have the answer. The problem is that calculating this quantity is not very easy, because hf is not diagonal, hf is very complicated. So you get some matrix which has all 4 elements, and then if you want to exponentiate a matrix, you are going to write the whole power sequence. Therefore, it's always easier to work in terms of mass eigenstates, because they travel linearly. So, if you want to look at evolution of level eigenstates, what we need to do is this should be I d by dt on this side. Okay, so don't look at this and correct this later. This should be, I cannot write on this side. So I d by dt of nu alpha nu beta is equal to 2. So effectively Hamiltonian is this. Okay. U times this matrix times u dash. So this essentially was a recap of what we know about vacuum motion in the two Neutrino framework. We got the matrix. So this is fine so far, because we take this time forward.
First, matrix in the center is time evolved, and u and u dagger are not time evolved.
They are constants.
That entire thing you're calling HF, or the matrix which is not time evolved?
Sorry. So okay. I made a mistake when I told you about it. This actually is the evolution, not Hamiltonian. So Hamiltonian is this part, okay, which is constant. Yeah, I'm sorry. This actually was the correct equation. Yeah. This is a time evolved equation, because I know my nu1 and nu2 had been time evolved like this, and I just did u dagger u1. Yeah, sorry. I thought I did a Hamiltonian equation, whereas I did an evolution equation. Yeah, so essentially, if I want to write down nu alpha and nu beta, I can just look at evolution of mass eigenstates and multiply on these two sides by u dagger and then.
Instead of evolving the flavor.
So I will always try to do this instead of writing of the whole powers. Okay, so now we'll come to the point where we try to see what happens to neutrinos when they pass through matter. Now this is a very subtle point. I suspect that most of you have not done field theory. So let me try to tell you first thing that one can understand without being a field theory first, and I just indicate what it is that is involved. I think at some point of time, later in the course, maybe in the class, where we actually come to the derivation of how to get this matter potential. Let me give you an idea of what matter potential means, why it will come in. So now in vacuum, our neutrino propagates. So let's say take a nu e. So in vacuum, of course, this nu e propagates like nu e. When this nu e will travel through matter, it's possible that it will interact with matter. So let me give you a possible interaction. Okay, so it can be simply that there are some electrons in matter. This Feynman diagram exists because we know that nu e can interact with Z's and electrons can interact. Okay, so this Feynman diagram exists. Now what will this mean? This means that, let's say this is a nu e with a momentum p bar. This is also nu e with momentum. Interactions exist, which do not change the value of this thing. See, of course, if you change the value of momentum, then you have got scattering. Okay. When the scattering occurs, the neutrino momentum changes. It can change the direction, it can change the magnitude. However, there is also this phenomenon called as forward scattering. Forward scattering does not change magnitude of momentum, does not change direction of momentum, but it changes its phase. Okay. It's like the kind of scattering you might have done in some quantum mechanics course. Let's say doing scattering across this potential. You have some particle coming of maybe wave vector k. It also goes away there k. But in this this small period where it is affected by potential, its wavelength changes. So it becomes k prime. I suspect you have done these kinds of problems in your quantum mechanics. Right? So you can have potential, and what happens is when the wave passes through the potential, the value of momentum changes only during this small interval, okay? And before and after it is the same. Now what does this mean? This means that if I did not have the potential, I would simply get k throughout. Since I had the potential, for some time I had k prime oscillations. Therefore, if I calculate the change in phase by using only this part, so let me call this as phi 1, and if I calculate the change in phase when I have some potential in the field, let me call as phi 2, phi 1 and phi 2 will be different. It is in this sense that a potential felt by a particle can change its phase. So there are different ways of looking at it. Okay? One way of looking at it is in terms of such kind of potential. Another way of looking at it is the following. Okay? Whereas does the phase of particle change? A phasor particle, Neutrino for example, changes as m square by 2e. Right? So we also know that the phase of particle as propagating changes as m square by 2e times t. T is the time taken when passing through the phase. So note that such a phase, okay, which had changed because of the potential, can now play a part in changing effective value of this quantity. So it changes effective value of m square by 2. Certain point as I give some time. So think of a potential problem. Okay, let's say potentially during this time, during time some t. A wave comes and I measure its phase at this point. Okay. If there was more potential, the phase would be phi 1. Because I put a potential here, during this potential area, the wavelength will change. Therefore, the phase finally will change. So, one way of looking at it for me is this, that the phase had changed because there was a potential. Another way of saying the same thing would be that, oh, during this time when the particle was passing through the potential, its mass value somehow changed. Instead of m, it became m plus some. That's why the oscillation was. Okay. Mathematically, these two things are equivalent. So this is fine. Right? So when there is a potential, you change the phase. And we are all interested in the final phase, right? Because final oscillation probabilities depend on change of phase. So therefore, this part of phase is very important. When will there be a potential? There will be a potential when there is something else interacting with these neutrinos. So whenever you have got something that interacts with the neutrinos, you will have a change in phase. Secondly, this interacting thing should be like forward scattering because we want to measure the phase, otherwise phase has no meaning. So two things are required. Firstly, something to interact, and secondly, forward scattering. No change in moment. So therefore, we should look at those interactions of neutrinos which can satisfy these two terms. So let me write it down. Two things are needed. One, you need something to interact. So some interactions. And second thing you need is no change in moment. It's called forward scattering. If this happens, then we can say that neutrinos experience a potential. Okay. So now let us see how neutrinos can experience potentials when they travel through matter. So let's try to write down all possible Feynman diagrams which can give rise to this. So let's first start with nu E. I already showed you one diagram. Right? This was mu E, mu E, electron, mu to electron. This is the thing that can happen. So I especially mentioned this is T bar, this is T bar. So there is no change in momentum also obviously. What else can happen? The same reaction can also happen with quarks inside protons and neutrons. But one can, for example, one can have mu E going to mu E, and this could have come from neutrons, protons. If you want to talk at the level of Feynman diagrams, you can talk about it not as neutron, proton, but as up quarks, down quarks. So you can have up quark coming and up quark going out, and always mediated by same protons.
All these interactions will have to be neutral current.
All are drawn on neutral current.
No, ones which we are considering for potential, they have to be neutral current.
No, so I draw your diagram now, which is not neutral current. So once I have drawn till now are neutral current lines. Of course, they are interacting. There is another way by which you can get this forward scattering for movies, but with charge field interaction, which is that you get mu E with the momentum P bar. What goes out is an electron with momentum P. It is some momentum K bar. However, the reason this happened is because there was an E with momentum K bar coming in, and then mu E momentum P bar. Now see what has happened. The mu E has come in with a momentum P bar. And mu E is going out with a momentum P bar. Okay. However, there are electrons in the medium with some other momentum K bar, and they can interact like this. So remember, see, this can happen for an electron neutrino. And now if I try to do the same thing for mu, okay, let's see what happens. So we write those reactions down, then let's see what happens. So I have mu. So this is of course possible. No? So mu E with mu E with Z electron this is this is also so mu
Z, and this is what is it, up, down, or in P, doesn't matter.
This also. Here I have the difficulty. I have mu of P, and if I want to create a mu minus going out, I need to have a mu minus coming in from the medium, but I don't have mu minus. Medium only has electrons, protons, and neutrons. So therefore, these interactions, which are called as neutral current, are present for all neutrinos. Okay. So this is for mu E, mu mu, and mu tau. This reaction, called as charge current, is only for mu. So therefore, mu will receive a potential from both neutral and charge current interactions. Mu mu and mu tau will receive a potential from only neutral current interactions. This simply because there are no muons in the medium. You only have electrons. We need electrons to come in for this to happen. So therefore, you will intuit that the value of this potential will somehow depend on what is the number of electrons present in the medium. Because you need electrons to interact with this medium. Okay. You can do the derivation nicely in quantum field theory, okay, but I will not do it. I will give you the reference so you can go and read this. So all I can tell you now here is that the potential that we get due to these charge field interactions, this Vc, is root 2 Gf times Ne. Ne is the number density of electrons. Okay. So right now just take these things as a given. Here on the other hand, for neutral current, as you can imagine, the potential that we get will depend on the number density of electrons, of protons, and of neutrons. Okay, the interactions are with all three, electrons, protons, and neutrons. Turns out that number of electrons is usually the same as number of protons. And they actually give exactly opposite contributions. And they cancel out. So therefore, for neutral current interactions, you will not get any contribution from protons and electrons because they cancel out. The only contribution you get is by number of neutrons. So that you have no control over. That will depend on what is your neutron fraction. What are the elements that you are passing through? If it's hydrogen, you have no neutrons, you are passing through lead, you have not many neutrons. So that gives rise to what's called as a neutral current potential. Okay. And again, I will give you the answer without telling you where it comes from. I will show you where the derivation. So this is Gf by root 2 times number of neutrons minus. Okay, so two things that we pulled out of thin air is that when neutrinos pass through matter, mu mu and mu tau get a potential which is equivalent to Vn proportional to number of neutrons. Okay. In fact, mu e also gets a potential. But in addition to this, mu e gets a potential due to charge current interactions, which also depends on number density of electrons in the medium. So once you accepted this thing, then the next part of the process is much simpler. So we will perhaps have some summary. So mu e to mu e is charge current potential plus neutral current. Mu e to mu e is just neutral current. Mu tau to mu tau is simply Newton. This is these are the values of potential in terms of number density of electrons and number density of neutrons. Okay. And this is a recent 5-year-old paper, okay, which has given it in reasonably nice details. Mind you, these things had been done by Wolfenstein in late 1970 and 1980. Okay. So this is not new, it's just that this guy has done it in a pedagogically more readable way. If you read this paper, you will be able to see exactly what's going on. Okay, so we'll stay with this. Okay. These potentials exist. So what do? We want to write down this potential in a matrix form. We want to study evolution of Newton. So normally, if you are writing in terms of nu e, nu and nu tau, you write down effective potential as this, no? Because nu e has both of these contributions. Nu has 1, nu tau has 1, and rest of the elements are 0, because forward scattering should not take you from nu e to nu. That's meaningless because you change the flavor. It's not possible. Okay. So now 3 flavors you will write it like this. However, right now we are dealing with 2 flavors. Okay, so let's not go into complications of 3. Let's look at different situations in terms of 2 flavors of neutrinos where the potential will come in. So let's say one flavor is nu e, the second is nu e or nu tau. Okay, what will happen? If I have nu e and nu mu, this potential will look like Vc plus Vn and Vn. Okay. But yeah, now we know that anytime we get identity, we can throw it out. Okay, so forget about Vn, all we need is Vc and 0. We are very happy. Okay, so actually the value of Vn doesn't matter when you look at oscillation between nu e and nu. So that is the situation for nu e. If we instead go to the combination which is nu mu and nu tau, which is what we have atmospheric neutrinos, for example. Yeah, so we just get V is equal to 0, 0 because there are only these two nu Vn and Vn identity, so you keep it. So therefore, even though neutrinos pass through Earth matter in the atmospheric neutrinos, whatever we studied about them till now remains valid because it is mainly a nu mu nu tau mixing. And in nu mu nu tau mixing, matter potential does not play any part. So whatever we did till now for atmospheric neutrinos was correct. It would have been wrong if they involved nu e something. Once you involve nu e, then you involve this Vc. But since atmospheric neutrinos do not involve oscillations with nu e, we are fine. Nu mu nu tau oscillations. Therefore, effective potential is 0. So you simply use your vacuum bar and results with vacuum are perfectly fine. Okay. So sort of a lucky break for us. If we wanted to use it, I would have introduced that matter oscillations from before. But this is it. So for atmospheric we are safe, but whenever we have nu e, then we have to do something. So, now let's go and try to solve an actual problem where we have nu e and nu mu oscillations, for example. So, let's say nu e is passing through matter, there is some mixing with nu mu, and we see what happens to nu e finally. We reach this concept called as MSW resonance at the end of this. Let me just mention it here. So what do we want to do? First we write down the Hamiltonian, then we exponentiate the Hamiltonian, e power minus IHT. That's our answer. Okay, this is how we always do. So Hamiltonian in the flavor basis. Earlier we saw that it was equal to this, no? U, this minus delta delta, U dash. That was the Hamiltonian. Now what has happened? In addition to this, we have potential, which is Vc 0, 0, 0. So both have been written in the flavor basis. So in flavor basis, therefore, this is complicated, but this is simple. Now if I want to go to mass basis, earlier one, this would be simple, but this would be complicated. So I have to use a U diagram for this. So let's stick to, sorry.
In the last slide, you gave those BC and VN expressions in terms of GF and NE. Those are in flavor basis.
The numbers. BC and VN are simply numbers. Number is a number. You don't know the basis. This was okay, sorry. This was flavor basis. Yeah. So the matrices were in flavor basis. Okay, because we saw that EE is this, mu is this, and tau is this. So in flavor basis, this has a very nice form. In the mass basis, this had a very nice form. So you have to stick to some basis, because when you introduce matter, which has a complicated form either way. So let me choose one basis of flavors. So in the flavor basis, this is our vacuum part, this is our matter part. So I can calculate this. This is delta. I know how to write U and U diagram in terms of cosine theta, sin theta, and so on. So you can multiply these matrices. If you multiply them, what you get looks like this. And reasonably messy, although not very messy. It's messy enough that you do not want to exponentiate it by using power series. You would still point out a simple way by which you can do the derivative with mass eigenstates. So something d for I delta t, and you get your factors. Because if you want to do DC evolution, this is complicated, right? So e power minus I HFT, and this means 1 minus HF minus this HF square by 2 factorial, and so on and so forth. Okay, which are, you can do it in principle, but that's not simple. That should be new 0, yes. So this should have been 0. So I want to avoid having to calculate this e power minus I HFT when I hit the matrix. Therefore, I have to find a clever way around this. There exists a clever way which will give us some nice solution. So what is the clever way? See, remember in vacuum, I had written down the flavor state in terms of mass eigenstates. And then I had this mixing angle called as theta, which was used as rotation angle. This cos theta, sin theta angle. Now what I do is I introduce what I call as mass eigenstates in matter. So constant density. I know we are talking constant density. I call, just like I had mu1 and mu2 as mass eigenstates in vacuum. Now I have mu1m and mu2m, which are mass eigenstates in matter. And they will always exist. Those will always diagonal as a matrix. So these two, mu1 and mu2m, are my mass eigenstates in matter. Once I have these two mass eigenstates, I can always write down a rotation matrix that takes mass eigenstates to flavor eigenstates. And this matrix has to be of this form: cos theta, sin theta, minus sin theta, cos theta. One simple rotation. So this theta I can now call as mixing angle in matter. So exact analog of mixing angle in vacuum, which was theta, now I call as mixing angle in matter, which is known as theta m. So all that has happened now, instead of talking in terms of mu1 and mu2, I will talk in terms of mu1m and mu2m. Right? So this matrix is then called as um, or you can call it as u of theta m. If people use different. So now it's straightforward. So now, what are these? What is this mu1m and mu2m? I did not tell you what is mu1m and mu2m. What do I want? In the case of vacuum, and I went to mass eigenstates such that the Hamiltonian became diagonal, minus delta plus delta. I want something similar. I want to choose this mu1 m and mu2 m such that if I go to their basis, the Hamiltonian is diagonal. I want 0, 1 top diagonal. So, what this means is the following. If I take my Hamiltonian HF, which was a complicated thing, right? HF, remember what? This. Now, I want to go to a basis where if I do a U diagonal U to this HF, then I get the Hamiltonian matter basis. So since nu is um times this, effective Hamiltonian matter becomes um diagonal HF times um. If this quantity is diagonal, I am very happy. Because then I can exponentiate very, very easily. So this is my aim. If I am able to find mu1 m and mu2 m like this, then the problem is solved. So let's see how the problem is solved, and then we try to find out what is mu1 and mu2 m. Let's say we are able to find this. Then what happens? If this is indeed the effective Hamiltonian, now see this looks exactly like the vacuum part, except delta have a label delta n. We will calculate delta n later on. Right now it's just a number. So once I find out this value of delta n, then I can simply write my evolution as this. So mu1 m will be e to the power r delta n t times mu1 m at 0, and mu2 m at t will be e power minus r delta n t times mu2 m. Okay, so things are exactly the same as before, except I have added this small suffix called as m. So therefore, if I am able to find out what this value of delta m is, then I am done. Very simple. Once I write everything in this form, I also know what evolution is. So even for nu e and nu mu, okay, remember we had this e power r delta t e power minus r delta t, and I do um diagonal and um on these two sides, and I find what is final value of nu e and nu mu. So exactly what we did for vacuum, now we are extending that to matter. And if I do that, just like what we did today, we saw that T mu nu was 1 minus sine square 2 theta times sine square delta t. If I do it now, I will simply get this answer. But T is 1 minus sine square of 2 theta m now times sine square of delta m times t. What we have done is reduce this problem to exactly what we had in vacuum. All that changed was delta m, okay, and this u is now dependent on theta m and not theta. So we need to find what is delta m and what is theta m. So what we managed to do is take our problem. Instead of exponentiating some complicated matrix, we went to the right basis. And in that basis, we know the solution is very simple. Of course, the final solution doesn't depend on what basis you use. So you have the solution almost handed to you over of that line. So you give me the value of delta m and theta m, I'll give you the probability. So constant matter density problem is basically the same as the vacuum problem, except for this change of theta. All we need to find now is what is this theta, how to calculate this theta. Right? So how do you find this theta? Things are straightforward. All that we did is we took the Hamiltonian and we diagonalized it. Diagonal Hamiltonian, you get diagonal Hamiltonian. That's absolutely good. So this was the Hamiltonian. Now when I diagonalize it, you know how to diagonalize two order matrices. That's the least definition. We solve this equation, which is Hn is um dagger hf times um. It's constant plus this. So I will ask you to solve this equation as a part of the group. Straightforward to solve. And I will give you the answers and we'll talk about what the answers. But this you can do, right? You can do your whatever. Secular equation or something. You can do that. You can find eigenvalues, you can find eigenvectors. So I tell you what the answers looks like. Okay. And you will direct answers on your own. That's the other statement. So firstly, let's look at what a mixing angle looks like. Theta m. It's kind of it's something that one should normally always remember. Okay, it's not trivial. Okay. If you have a matrix which is A, B, B, C, okay, and if you have to find out the mixing angle, it diagonal like this. Okay. It's always tan 2 theta is 2B divided by C minus C.
Please give the previous slide. This one out denominator is correct. 2 will not be there. Maybe I did
Yeah, sorry, I don't know why.
Yeah,
yeah. So in fact, yeah. Once we look at what this will look like, then yeah. Let me see if there is a mistake. So let's come. Okay. So if I have a matrix like A, B, B, C, okay, which is a symmetric matrix. It's a rule of thumb, quick trick, that the mixing angle required to diagonalize this is always given by tan 2 theta is 2b divided by c minus. So that's always. Okay. Now let's go back and see how it matches with our. Okay. So 2 data. So actually what I missed is a 2 factor at the top. Yeah, so this factor. Bottom 2 is right, the top 2 is right. So this should have been tan 2 theta m, therefore. So tan 2 theta m should have been equal to 2 delta sine 2 theta divided by 2 delta cos 2 theta minus bc. So 2 times this divided by c minus a. So tan 2 theta is this. So what this means is that when neutrinos pass through matter, effective mixing angle changes. So initially mixing angle could have been theta. Now it becomes something else, theta m. We'll come back to this. Next, we can find out the eigenvectors, eigenvalues of this matrix. Difference in eigenvalue is 2 times delta. So you can find a value of delta m. That turns out to be this. Again, is something that you can prove by simply diagonal in the matrix. So looks messy, but if you look at this carefully, it's basically here also I have this factors of 2. So I should basically change this slide once more. But anyway, let me give you the. So if I want to give you the value of delta in matter, so I think I have done some error in use of delta in matter. This should be easy matter. you actually diagonalize this, you can correct my mistakes. It will be VC by 2 here. So it's, remember, VC goes to 0. When VC goes to 0, this is simply equal to 10. So that's at least one thing that can do. And as VC changes, the value of delta changes. So these two are the mixing angle matter and delta is perimeter. So what has happened in matter is, effectively you have changed the mixing angle and you have changed the value of delta. So let's look at some features of this. Okay. So let's look at this tan to theta. Let me write it again for that. So tan of 2 theta n is equal to 2 delta sin 2 theta divided by 2 delta cos 2 theta minus. So let's look at what are the values that theta n can take in principle. So one thing to note, of course, is that when VC is equal to 0, it matches. Okay, it is just equal to tan 2 theta. So let me try to plot. So this is VC and this is tan 2 theta. So at VC is equal to 0, this is simply equal to tangent to theta. This is vacuum. This is 0. So this is, so which is tan 2 theta. Now what will happen? Let's say theta is positive, some small number. When VC increases, the denominator will decrease, numerator will increase. Okay, so let's say no, delta is positive, the theta is like 10 degrees. So this is a positive quantity. This is a positive quantity. VC is positive because it's remember VC was root 2 GF times density of electron. So it's a positive quantity. So as VC increases, tan 2 theta increases. In fact, when VC is equal to 2 delta times cos 2 theta, the denominator becomes equal to 0 and tan theta actually goes up, tan 2 theta. So if you want tan 2 theta, then I start at this point, it increases as VC increases, and at some point it goes up. Okay. After that, it will become negative. First it will become negative but very large. So it will come out from this end, and then as VC increases, it becomes smaller and smaller, but still stays negative. So as VC goes to infinity, this quantity will be very small but negative. People agree with this? This is positive, negative. VC is large, which is almost 0. So it starts with this infinity and comes down. Okay. So there is something special happening at this point. At this point, theta is 45. At this point, theta is 45. So this is the point where theta is 45, which means that tan to theta is infinity. So what is happening? So theta therefore started from its value, let's say 10 degrees. It increased, it went to 45 degrees. After that, it increases above 45 degrees. Okay, it goes to above 45 degrees, tan theta becomes negative and dark, and then it is moving slowly towards 90 degrees. If you look at tan 2 theta, as it approaches 90 degrees, it stays negative, but it's smaller and smaller. At 90 degrees, that's equal to 0. So, as I am writing tan 2 theta is perhaps sometimes nice to write in terms of theta, of let's say tan theta. So, this is VC, and write tan theta, and now we see what happens. It initially started increasing. At some point it passed through this 45 degrees, and then it narrowed down again to 90 degrees. So it went up first, and at some point it became 90 degrees. So this is 90 degrees, and this is the point where it became 45 degrees. Another way of writing it is drawing the quantity which is sine square 2 theta. So and I will ask you to draw these quantities in your assignment. I just indicate to you what the shape is. Okay. Now see, sine square 2 theta is again a quantity which will become maximum at theta m is equal to 45. That is 1. So again it should start increasing, reach 1, and then as theta m goes beyond 45 degrees, it goes down and goes all the way to 0. So it will decrease. So look at these angles in these 3 different ways. Okay. If you look at it in terms of tan 2 theta m, that goes up. If you look at it in terms of sine square 2 theta m, it reaches a maximum, and tan theta m, it reaches some kind of a inflection point. Just for point. What's crucial is this. What's crucial is that at some point, this theta m is just maximum. So what does this mean? If we look at a probability for matter oscillations, so if you look at, let me see if I can find it by going what is on that. In oscillations in matter, the amplitude was sine square 2 theta m. So what I have shown you is that at some value of Vc, theta m becomes 45 degrees, always. So what this means is, even if you start with a very small value of theta, given the right amount of matter density, the mixing angle can become maximum. So say you are in vacuum, and in vacuum you only have very small oscillations. You can always put enough amount of matter such that oscillations are very, very large, amplitude equal to maximum. So just changing of matter density would change the amplitude of oscillations. This is very important. You can start with mixing angle of 0.1 degrees and it will become maximum at some point, given the right matter conditions. So this point where this happens is called as MSW resonance. So this is named after BKM, Smirnov, and Wolfenstein. So this point, where this sine square 2 theta m is maximum, is called MSW. That's MSW resonance. And we know what happens at that point. That is the point where the denominator is 0. Okay. So, which means that 2 delta cos 2 theta is equal to Vc. So I can write it as 2 data is theta n square by 2u cos 2 theta is equal to Vc. So that's root 2 gf times n. These are all accumulated. So therefore, if you know neutrinos with some mixing angle theta and some delta n square and some energy, okay, then for the right value of matter density, you will have this resonance, and your neutrino will oscillate with amplitude equal to 1. Everyone sort of appreciate the significance of this. Right? This was a very big thing. Small angles becoming large because they become also more observable. When we talk in terms of iono electron, we need to talk about 3 neutrino oscillations, and we'll see why the resonance is very important even in that case. Here, for example, it will be of relevance when you talk about solar neutrinos, because inside the sun you start with very high density. So it's like you high density is high value of Vc. Okay? So you start somewhere here, okay? And then you start coming out like this. You have to reach vacuum because vacuum is here. So at some point you have to pass through a region, okay, where oscillations are massive. Okay? So therefore, the sun oscillations in the sun will be more complicated than those in atmosphere, because it will pass to this region. So even if your mixing angle was very, very small, still during the propagation at some point of time you will have passed through a region where oscillations were very, very large. So as a result, the sun becomes so much more interesting problem to follow rather than simply atmosphere.
But you are talking about constant matter density. So you are thinking about like at a constant point of time, or I mean the neutrino is coming out from the core of the sun. So if I think at the distance from the center of the sun, the density is changing. So neutrino is coming at some point at some time, and it will facing an instantaneous density or number density. So that will determine its oscillation completion.
So good point. So what I showed you today is for constant matter density. And I just used the motivations to say that inside the sun this will happen at some point. However, inside the sun, more complicated things are happening, which is that the mixing angle changing as a function of time. So we have to take time into account also. So in fact, we'll spend one whole lecture, a part of the next one and a part of the next one also, dealing exactly with this problem. You have to be able to solve a problem where matter density is changing from time to time. Therefore, it is not simply that you sometimes have this region, so you get large oscillations. It's not just that. Okay. So we will see how to deal with that. So that's in fact a very important part of what we are doing. Okay. So yeah. So we saw what happens in vacuum, which is what we know, and we saw what happens at this MHW resonance, okay, for this theta. When you go to very high densities, what happens? We actually saw it here. At very high densities, sin square 2 theta is 0. Clear, because this goes to 0. So at very high densities, you have no oscillations. Okay? You hear this in literature sometimes as saying that at very high densities, oscillations are suppressed. Okay, what this means is that the sin square 2 theta is 0. Okay? Therefore, there are no oscillations. However, note that if you look at tan 2 theta n, it is 0 with a minus sign, slightly negative. Okay? So theta is not 0, theta is 90 degrees. Okay? So this is the point I want to. Okay? If you look at tan theta curve, passes to 45 degrees and increases to 90 degrees. So at high densities, mixing angle becomes 90 degrees, and the oscillations become equal to 0. Okay, so this is one point that okay, so no oscillations, but doesn't mean zero mixing angle. It also means 90 degrees. Another thing I want